It's a question from JEE Mains. It says that there are two planets, mass M and 9m, radii R and 2R respectively, center to center separation of 8R. This is a given data. Take the two planets fixed in position. Now see, a satellite of mass small m is projected. Let's say a satellite of mass small m is projected from the surface of this planet M of mass m directly towards the center of the second planet. Directly towards the center of the second planet. The minimum speed v that this satellite should have so as to reach the surface of the second planet is what the question is asking as this expression. Now I'll drop the question off. You take down the question from the preview of this video. The situation is something like where the satellite that has been sent from this you can say planet of mass capital M, what would be the challenge for this satellite to reach the second planet of mass 9m? What can be the challenge? The challenge is simply one thing. If you presume challenge can be only one thing, the gravitational force of attraction between these two bodies would be directed this way for this body and directed this way for this body. These forces of gravitational attraction will keep this particular body experiencing this, the satellite of mass m. Let's say I keep this as a point A and I take this as a point B. Now imagine at point A and at point B, and the satellite has been launched, let's say, from a radius of r over here, and this is the planet of mass m. So in this case, let's say the satellite is launched from this position with a velocity v with a mass m. The challenge for this particular satellite is that midway somewhere, this satellite of mass m will experience gravitational force of attraction from this planet as well as from this planet. And this gravitational forces of attraction, let's say this F1 and F2 or F2 and F1, whatever you call, till the moment they are not equal, then the larger force will dominate the motion of this planet. The acceleration will be guided towards the larger force. Somewhere in between, it will so happen that the acceleration of this particular satellite is zero, because F1 will turn out to be equal to F2. At that point, the velocity will not change. That minimum velocity should be achievable by the satellite so as to proceed forward, and then as it moves to the right side, obviously your F1 becomes greater than F2 in this region, whereas in this region your F2 is greater than F1. So if that is the case, then F2 should pull it back, but it won't pull because the net energy would be diverting it or drifting it towards the planet B. So as long as F1 is greater than F2 from this point onwards, then the satellite keeps moving towards the planet B. Now see this, F1 equal to F2, this critical force equilibrium condition is attained where? Let's say F1 is equal to G small m capital M by a distance of x. We, let's say, do not know the position of x, and then the remaining distance from here till here would turn out to be 8r minus x. So these distances would decide the equilibrium of the forces. So force F1 can be said to be equal to G capital M small m by x square, and should be equal to G small m into 9m by 8r minus x whole square. This equality gives us a calculation. G capital M cancelled, small m, GMM cancelled, gives us 8r minus x whole square is equal to 9 times x square. GMM cancels, and that means 8r minus x is equal to 3x, and that means 8r is equal to 4x and x is equal to 2r. This is the distance. This x is equal to 2r, and therefore this is going to be equal to 6r, where the acceleration of this particular satellite is going to turn 0. Now what happens is the energy that it started with, the total energy that it started with, will be half mv square minus g capital M small m, g capital M small m by capital R, the distance between these two bodies initially. Now there are three particles in this entire play. There are three things in this entire play: this planet and this satellite. So this is the gravitational potential energy between these two, whereas these two also have a gravitational potential energy, and that is going to be g 9m into small m by the distance between them. Now that means 8r minus r. This is going to be a 7r. So this is the net potential energy between any two pair of bodies in the system. And for the satellite, this is the net total energy on the satellite should be equal to, let's say, the velocity at this point is equal to some v1, that means half m v1 square, and then half m v1 square minus g minus g capital M and small m, g capital M and a small m over here with a net distance of 2r by 2r minus is the potential energy for this particular body and this particular body at a distance of 2r minus g 9m into small m by a net distance of 6r remaining between the two bodies. Now when we solve this equation, what exactly do we expect? We expect that the velocity of v should be non-zero, as well as the velocity at v1 should be non-zero. If this is the expectation, then you are going to have a terrible calculation. If suppose the satellite is supposed to reach this second planet of B straight head on, if it is to go forward, then this velocity v1 should be non-zero, and hence this kinetic energy should be essentially positive. It's a must. It should remain a positive. And for that, what should happen is the sum total of the other energies when taken on one side should turn positive. That means if I take everything on one side, I am going to get half mv square minus g by capital R. If I take as a common element, then I have a 1 from here, and g by R means plus 9 by 7 from left side. And on the things on the left hand side will turn on the left side as, let's say, minus half with a minus half. I have taken minus out, and this is going to become positive when it goes to the left hand side. So this is going to become half, and this is going to become 9 by 6 means 3 by 2. And this sum should be at least greater than equal to 0, and that means this thing should be positive. So that means if half mv square has to be equal to g by R into let's take an equality over here, 7 into 2 14, that means 14 plus 18 minus 7 and minus 21, and that gives us g by R into 14 plus 18 is a 32, 32 minus 7 25, 25 minus 21 is a 4 by 32 minus 7 25 minus 21 is a 4 by 14. And now if we simplify, you see we are going to have a reduction over here as a 7, and m cancels. That means v square turns out as equal to g by R into a 4 by 7, and therefore the v is equal to root over of 4 by 7 into g by R, and therefore the value of a is equal to your 4, and is the answer of this question, and is based on energy equality. In fact, it is similar to the escape velocity calculations, though not exactly. It's a case of escape velocity. I repeat, look at the calculation once more, and this is how it goes. Kinetic energy at the surface of the starting planet A, kinetic energy, potential energy due to this planet, potential energy due to the second planet. Now midway, where it loses its you can say acceleration due to force equilibrium, gravitational force equilibrium. What happens is, this is the kinetic energy, this is the potential energy due to the planet from which it left out, and this is the potential energy due to the second planet at a distance of 6 arc coming on. Therefore, this equilibrium brings us to a condition where this kinetic energy should be at least positive, it cannot be zero, and hence this particular thing, and hence this, the minimum value of the escape velocity from this planet therefore should be this. Thanks for your patience, and see you in the next question. Stay subscribed and stay revised.